Here we go. Packet 6, class 25. You draw about 25. Let's say average is at least 25 videos a packet. So, we're looking at 150, 160 videos in this series. I suppose somebody could just watch these and learn some physics. I mean, it's all public. So if you got a little brother or something or sister that lives out in the sticks, they could learn some physics free. I'm going to run the class and I'll make it better starting in the fall. And then 2022 fall, I will be full-time just doing it with studio. I'll have my studio set up. It'll be a lot better than this. This is like beginnings. All right, we are recording. Yep. All right, let's see what's going on here. Little happy faces. Little happy faces. Most of them are happy. What's going on? A bunch of happy faces? What? Well, it looks like it's some kind of, it's actually got a pattern to it. It's representing something. What? Oh, 3 more sessions. There's some angrier ones in there. 3 more sessions. Okay. Including this one. Actually, it's 4. I forgot about the key when I make the video key for everybody on Wednesday next week. Is it Wednesday? Or is it Thursday? Maybe Thursday. I'm sorry. Thursday next week, I'll make a video key of the test. So, no. It's Wednesday because we're going to do Blue Day. Yeah. So anyway, whatever. I'll figure it out. Someday next week, there's the extra one. That's the video key for the test. What else we got going on? Weather's looking kind of, I was starting to get hope yesterday, but then it rained pretty good this morning and everything got soaked again up at school. So as far as the West Lawn goes, so unless it's just pure sun from now on, I think Friday we're probably not going to be on the West Lawn, but we will be, and I'll start serving dogs about 12:15 Friday. Dogs, we'll have some dogs, and these are the best dogs. I'm going to go out tomorrow and buy the best dogs I can find. And I'm talking ballpark Franks is minimum. That would be the cheapest kind of dogs I'd get. Maybe get those Nathan's dogs, So come by the high school about 12:15. We'll eat at 12:30. This is not Friday. This is this Friday. This is coming up. Yeah. At 12:30, we'll start taking pictures, group shots. Okay. We may all go out to the West Lawn. We may do it in the classroom. Depends on if it's decent at all. We're going to go on the West Lawn and take a big picture. You want to be in the picture, right? I told you already that I'm going to pass out the packet organizer today. Here we are on the 19th. I'm passing out the organizer not tomorrow, but on Friday. For you, it'll be available tomorrow night, late. Oh, tomorrow night we'll be Zooming to help you on the take-home test. We'll go over a problem today on the take-home test. What else we got? If you bring a dessert Friday to the lunch, your meal, somebody already brought their dessert. Your meal will be free. Otherwise, it's $3. I mean, it's pretty cheap. Chips, hot dog, Coke, probably some cheese. I don't know if I don't know if I can do chili. Last time I try to do all that, I blew a fuse in the building and then the electricity all went out. So for my room, which then it ruined it. So a little nervous. Okay, let's talk about new equations. Last night, I did 2 big things. I graded everybody's like Blue Day and I graded all this extra papers that have been building up, just old stuff coming in. So I'm caught up on grading, put all those grades in, and then I put together 3 new equation sheets. Equation sheet side 17 starts off with the free body on the inclined plane, and then shows it's head to tail. Okay, you can also do it head to tail. There's Newton's third law, and there's Sophia. Sophia, I went ahead and picked hers. I thought was there were some good ones on that one, but think about if you take a picture of your worksheet, then it comes out too dark. So she must have scanned it or something because it came out light. And so I thought that fit nicely, probably better job than I did, so now she is officially ensconced in the physics program, her work there. She can show her grandkids one day. Side 18, we start off with the elevator equation. We have gravity, general relativity. We talk about the principle of equivalence, and there it is, kind of in a nutshell. Gravity is equivalent to acceleration. Once you understand that, then you can start to pick up, curvature of space-time and all that, which you're not going to take that class until you're at least a junior in college. And then we have Newton's universal law of gravitation. We'll talk about that today. I changed this. This one has it as a little r, but to tell you the truth, little r, and that's cool for that one. But here, when you're talking about the G of a planet, and we'll get to this problem later, it's actually a capital R there, because that capital R means that it's a constant. Like we know what the Earth's radius is. I mean, it varies a little bit, but in general, to 3 siggies, we know the Earth's radius. We'll get to that problem later. And then I use this table myself when I'm writing physics problems, like astrophysics kind of questions. I thought, why not just give it to you guys so you have a reference? So I left off Pluto, but it's not really a planet. So there's the 8 planets and the moon and our moon. And everything is relative. These are all planetary facts, and everything is relative to the Earth. Okay, the Earth being one. So you can look at this. You got for each planet. It's a handy reference guide. For each planet or solar system, we got mass, diameter, density, gravity, escape velocity, rotational period, length of day, distance from sun, perihelion, aphelion, orbital period, orbital velocity, orbital eccentricity, obliquity to orbit, surface pressure, and number of moons. Okay. Mercury has no moons, neither does Venus. But look at this. There's some crazy numbers here. Check this out. The surface pressure. I think I screwed that up. Oh, well, the surface pressure on Venus is 92 times the surface pressure of the Earth. So you walk out and on Venus, you go out of your house on Venus and you're going to get squooshed. That's why we're never, you can't do anything about it. It's a runaway greenhouse effect. I suppose you could somehow fix their greenhouse issues they have, climate change, but you're never going to be able to hang out on the surface. It's going to crush you like a can, like a soda can on the surface of Venus. But we are going to inhabit Venus. For instance, we talked about this in class. If I'm standing on the surface of Venus somehow, where is the ocean? Sorry, I got to turn you up. Where is the ocean if I'm standing on the surface of Venus?
Would it be up?
Yeah, it's above you. The problem is it's made of sulfuric acid. So we'll have to orbit. We'll have an atmospheric city on Venus, a cloud city, I guess you'd call it, kind of like in Star Wars. We'll have a cloud city above the clouds, and actually the temperature on Venus is like some days is like 72 degrees Fahrenheit out in the atmosphere. So it'll be pleasant. The problem is there's no oxygen, but we can probably do something about that. We can work with what they got. Venus is really, except for that daggone greenhouse effect, is probably the most like Earth, more than Mars. Okay, anyway, so this is kind of a nice little table to have as a reference. Not that yet. Hold on. Let's keep going. Side 19 looks like this. Starts off with law of sines, which we use that on our statics problem. So there is a truss. The problem with, I was looking up, we're going to Florida this summer, and I thought, well, we're going to go by Memphis. We got to cross the Mississippi, and you can't cross the Mississippi now on I-40. I thought, well, is that going to be done in time? Now they're talking 3 weeks, a month of work just to get it stable enough to really start working on it. It's going to take a year or two to get it fixed. But that's all trust. That's all a trust problem. And somebody didn't do their physics right or didn't maintain it very well, because now it's cracking. There is the nuts and bolts of if it's a triangular truss like that. And that's how you work that problem. Like a table looks like that. I got a FedEx box on it. A lot of tables look like that. That's the kind of forces you have. If you go, hey, don't jump on that table, well, you can look at it and go, I can tell how many pounds it could handle. That's what this is telling us. The law of sines is how you go on, but the fast way of doing that one. So that comes in handy in case there happens to be one of those on the test. There is one of these on the take-home test. You can use this as your guide. And then I went ahead and put this friction. I have not put friction on an equation sheet before, but I thought, man, we spent so much daggone time on it. So I thought we need to put some more. We have friction equations. I said friction revisited because we already put the equations for friction. But this is the first time I put LDFs on there. So anyway, I'm thinking this is what you need when you go to college, right? I'm trying to find something that'll help you in college, not just my class. So I thought, well, they need it. Okay. General announcement here. I put this up third hour today. I'm selling my iPad Pro. This what I use every day, and my case, and it's a nice. I mean, this case is really. I've been very happy with this. I have no problem with this iPad. But the only problem is it's out of space. I cannot gather any more space in here. So I'm going to wipe it clean for you. I'll leave stuff on them if you want, some of my applications, if you want them, I suppose. But I'll wipe everything else out so you have plenty of room. You have 64 gigabytes. There's no problems. Never was dropped. It's never been left out in the sun. I treat it like it's fine china because I know if something happens to it, I can't teach. So it has been well cared for. Now, Apple said they give me about $500 for it if I just send it back in. I thought, well, why not just give it to you? So if you're interested, then DM me and we'll discuss. But I'm not coming down that price because I can get that tomorrow from Apple. But I want to buy the same iPad Pro for my June project, but I want it to have 256 gigabytes. So I have none of this buffering stuff going on. But this ought to be enough for you. It'll get you through college. Or if you're a sophomore or junior, it'll get you through next year. Every teacher will accept, they should, unless they're Neanderthals, they should accept iPad work. I mean, if I accept it, everyone should accept it. So you would save money. I think for the whole thing, I spent like $1,200. If you include the case and all, about $1,200. I'll give it to you $500. It's a couple years old, but it's still state of the art, really. Okay, so I went around and I checked this. Now I'm showing them both today and tomorrow. Tomorrow I'll check 7, 8, 9. So if you want to keep up with the class, you should have the take-home test 3, 4, 5, 6 done, and the 7, 8, 9 done tomorrow. And then tomorrow night you're in good shape for the last page. We're going to pretty much go over together in here. We'll go over one of them today. We'll end up going over pretty much all those problems together, so I wouldn't worry about the last page. Okay, now we have this demonstration. I'm going to stop the recording because I don't get copyright issues. And this is demonstrating, and I'll put it in the comments below in the screenshots. So let's pause recording again. All right, so we watched that demonstration. Pick that up in the comment section below. And let's go back to sharing. I can get this thing worked out. All right, so we're sharing back on the screen again. So yesterday we talked about this, the one where you're illustrating Newton's third law, and so that's a 5-second problem. Now you can go back and look at that video, and then we ended up. The last thing we did yesterday is we went from showing that the conservation of momentum is basically just Newton's third law. So Newton was double dipping there. He was getting credit for both when they're really the same thing. And there is 6-9. We finished that. We're not going to work number 6 because that requires center of mass. I'm going to include center of mass. The last equation sheet you're going to get for spring semester is equation sheet 20, which you'll get like this weekend, because that has some stuff we're going to talk about tomorrow with impulse and all. I want to talk about it first, then I'll release that. And that also has, I also put center of mass on there, even though we didn't really get into it, but that is the formula for center of mass. Okay. So first thing I want to do is, and I sent them to the board on this, but the first thing I want to do is I want to work number 14. And now we're back to 6.8. I want to do number 14 together. Well, I'll have you at the board. So hopefully you can read that. But we have Joe Dynamo being pulled up a ramp. So 22-degree ramp. This is a good problem. I wish I had put this on the take-home test. But when you hear me say that, you think, oh, that means he's going to put it on the actual test. So put a little TST beside it in case this might be my surprise question. One like this. It's got a lot of good stuff in it. Okay, so I'm going to hit pause again, and I want you all to go to the board. I want you to try and at least do the a labeled free body diagram, okay? And then we'll come back together and talk about the equation. Okay, so hitting pause on. So force a pull up. We are now working on this free body. Force a pull up the incline, and then we have friction back. And I know my lengths are probably not right. And that's okay. I mean, if I was doing head to tail, it would force me to get the lengths right. That's F sub K now, not F sub S. And this guy, I'm making him a little bigger. Okay, there's my force of pull. Okay. Now, I went around and gave an insta stamp if they did this. If they turned that MG into a right triangle without me having to tell them. Hold on. That's the force of kinetic vac. Direction of motion's up the incline. So this may come as news to you, but the force at an angle is the hypotenuse of a right triangle. Go and make that green, I guess. I always want to color it in. Notice since I tilted my axis, I only have one right triangle. If I didn't tilt, I would have had 3. These are the kind of tricks that you're going to be at college and you'll be sitting next to a kid from Durant, and the teacher will the professor will give some kind of problem like this, and the kid will say F equals MA. But they don't really, a lot of high schools don't really go into the details of, because I don't know, they don't. So you're going to have to help them, help these kids around you to understand that you got a tilt axis. It helps you. It makes your life easier. All right, so then we throw some numbers at this. I don't know why I pick on Durant. Nothing wrong with Durant. 1,000 newtons. Never been there, actually. What else do we know? We know he's 992, which just seems oddly specific. But Joe is 992. No, that's not kilograms, that's newtons. What else? Do we know anything else? Oh, Okay, we'll have to use some of that in a minute. I think that's all we know as far as forces. So now we go through and we're going to determine, we're supposed to determine what is mu sub k. Okay, so we go, let's get rid of that. We go summation of force. We're not going to work all this, but we'll at least set it up. Summation of forces in the x equals max. Okay, so force of pull minus the friction minus what?
mg cosine 68.
Ah, you got it. Okay. mg cosine 68. That angle right there is 68. This guy. Because it's complementary to the 22. And if that doesn't make any sense to you, you need to go through and do the geometry. Little double triangle geometry there. We talked about it before. Equals max. Okay, great, but I don't see mu sub k anywhere. Where's mu sub k? I'm supposed to solve for that.
Isn't it in the kinetic friction?
Yeah, so I got to, thank you. So I got to open up that kinetic friction suitcase. And we said F sub k was mu sub k times n. All right, so I'm trying to solve for that guy. Well, that helped me someplace, but now I don't know what n is. N, I mean, it didn't tell us what normal force was. So now somebody besides Sophia, somebody else tell me, what do I do now to find normal force?
Wouldn't the normal force just be 992? Or
Well, you would think so. Keep going. 992. It's not flat. It's not horizontal. If it was horizontal, I agree. But this normal force is not congruent to mg.
So it would be 992 plus mg sine 68.
Okay, so I hear kind of what you're saying. So it's in the x, okay, in the y direction, the tilted y direction, summation of forces in the y direction, it equals 0 because, you know, Joe Dynamo's not levitating, is not sinking. So we have two forces in the tilted y. We have n, all of it tilted, minus mg, like you said, sine 68, and that's going to equal 0. So is that okay if I just make them equal to each other, right? So therefore, n is equal to mg sine 68. Aha. And we know mg is 992. Looks like we got everything. Uh-oh. What is acceleration? He didn't tell us that either. How do we find it? Somebody besides Io or Sophia. The hint, the color I did it in. Anthony's usually pretty quiet. He could jump in there. Eric's surprisingly quiet today. Bennett usually has something to say. Takagi, I don't hear from Takagi very much. He needs to talk. How about Anthony? Want to use? You got a bunch of dudes here. One girl. Seven dudes and a girl.
Do we use second orange?
Yes. So Anthony comes through there. And so we have, so second orange will do this. And we're not going to run the number. We're going to stop here in a minute. But second orange will do this. We know delta X is, what does it say? 15 or 5. We know delta X is 5 meters. And then we have this odd time. I have no idea. I think I was trying to, when I wrote this, I was trying to force them to do Sig Figs. Sig Figs used to be such a, oh God, I was a tyrant about them because I came from AP chemistry, where back in the 80s, Sig Figs were huge. Now, not so much on the AP chemistry exam. They kind of relaxed. So yeah, right. And now you guys, I'm not going to insult you by going through every little bit of second orange again. And now it looks like we can do it. We have one equation, one unknown. And then you'll have your answer. Okay, so that's good enough for that. You don't need to work it all out. Just you got enough for your. Oh, by the way, tomorrow night that's why I'm not handing out the packet organizer tomorrow, because I want to go through each sheet and I want to know what we do tomorrow in class. Then I want to go through each sheet and tell you what you don't need to worry about. Okay. Like obviously you don't got to worry about 615, 614, 613, maybe 612 on Monday a little bit. But don't throw those away. You can pull those off the back. And I'm still assuming you're going, I didn't give you a slot. I guess I could. I didn't give you a slot to submit that online, but I guess I could. You'd have to, when you do it, I want one daggone PDF. I don't want 12 PDFs, please. So you got to know how to do it. You just go to the scan, go to notes, go to scan, and just it'll line them all up for you. And you send in one. You send it once, not 12 times. I prefer, though, tell you the truth, that you would just drop it off at the porch because it's it's easier. But I understand some people can't do that. More about that next week. So the packet organizer, like ones like this, we did I'll try and be more specific on what all needs to be done on each problem, each worksheet. May be in 2 pages. Okay, we still got 12 minutes. The last thing we're going to look at is 610. Now, 610 will definitely do a little bit on the very first day in June. We're only going to hit 2 of the problems today. We'll do a little more in June. We've done more on, I thought we'd be doing that universal gravitation in June. I didn't think we'd get to it at all here, except in first hour that day, it came up, and then here we go. So basically it comes down to that equation and some manipulation of that equation. So let's look at number 3. We're just going to set it up. We're not going to actually work it. Oh, I want to show you something cool on 3 though. All right. So we got 3 more things to do, and I got 12. I got to hurry. How much force is required to keep the sun to keep the Earth in its orbit? So we go through here. See what's buffering? It's because we're out of room. So we go, okay, FG, it's plug and chug basically, equals capital G, mass of the Earth times mass of the sun all over the distance between us squared. I don't know why they make it a small r, because that's a constant in this case. So constants will make capital. Now, plug and chug, right? Mass of the Earth, G, of course, is that. Stick that in there. Mass of the Earth, mass of the sun. Lots of arrows here. Distance between the center of the sun, the center of the Earth. Okay, plug and chug, you got the answer. But let's do something more interesting. Let's do back of the envelope. And let's get a ballpark. Back of the envelope gives you a ballpark. And a lot of times, like if I'm driving down the road, I'm thinking about this. I don't have a calculator, so I'm going to just run the numbers in my head. All right, so here's how you do it. You say FG is approximately equal to, well, G is about 10 to the negative 11th. No, it's actually closer to 10 negative 12. Because it's yeah. So it's about 10 to the negative 12. That I'm not putting units. I'm just putting the powers. The mass of the Earth, we're on the order of 10 to the 24th. The mass of the sun, we're in the order of 10 to the 30th. So the sun's about 1,000,000 times more massive than the Earth. Good number to keep in head. Yes. It looks like the Earth. I'm going to go 10 to the 25th on the Earth because it's closer to 25th and 24th. 10 to the 25th. And then the distance between us, about 10 to the 11th, is my power there. But I got to square it, right? Okay, because you're squaring the radius. So now I run through my numbers. The top three I'm multiplying. I'm going to multiply this by this times this. When you multiply numbers, what do you do with the exponents? If their base is the same, you add them up, yeah? So 25 plus 30 is 55 times negative 12, 43. So on top, we have 10 to the 43rd. This beats getting your calculator out. And on the bottom, we have 10 to the 22nd. Oh. Okay, I screwed up. I just realized in third hour. Oh, well. Is that right? Add them up. 55 minus 12 is 43. Okay, so that's why my number was off. Okay, so then I subtract, right? So that's 10 to the 21st. Yeah. So this in newtons, this is the approximate amount of force that the sun is holding the earth with. Keeps us from going off tangential. Okay. Keep going. Still got 8 minutes. That's enough for that one. You don't need to go back and do anything else on that. We're only doing 2 problems on this whole sheet. Don't mark through the rest though, because if you're coming in June, don't. I had a student from Washington State that's going to join us in June. I don't know if you guys knew Sasha Peck. Sasha's going to be with us in June. Dr. Peck's son. You may know Sasha. I've known Sasha since he was a little kid. And so he was always saying, I'm going to be in my class, be in your class one day. And now he gets to be in my class. At least for 12 sessions. So join us. It'll be fun. All right, now we get to number 4. Use Newton's universal law of gravitation to prove that G is 9.81. Okay, so here we go. For me, my weight is mg, and that is the force of gravity on me. That equals big G, my mass times the Earth's mass, divided by, and I'm standing on the Earth, so radius of the Earth squared, which is pretty much a constant. Notice what happens. The green kill pin, my masses go away. That's why it doesn't matter whether it's a grand piano falling or a ping pong ball. If I take out air drag, they're going to fall at the same rate because their masses get canceled. This shows why it is. We tried to explain it with inertia and all that, but the equation tells you that. Newton must have freaked. And at this point, you plug in the values we already have. Oh, by the way, the radius of the Earth is 6.37. 6.37 times 10 to the 6th meters. You square that, you plug in the mass of the Earth, you plug in G, and sure enough, you find that G is equal to 9.81 meters per second squared. Okay, now we got 5 minutes. Now let's go to the take-home test. The back, save it. Don't do anything on there. We'll come back to that in June. And now we have number 15 on the take-home test. Felix Baumgartner, we talked about him jumping out of the gondola, a perfectly good gondola. He jumped out of it at about 30, well, I did it to 4 Siggies, 38.97 kilometers. World record. So he jumps out. Now, here he is. he was so high up that he could see the curvature of the Earth. Okay, so he's up here at 38. His altitude is 38. We call that H. But you don't do it. You don't plug in 38.97 for your radius. That's from the center of the Earth. So you have to add to that the RE. See what I'm saying? So your equation, it says, what's his G? Well, now we've already established, this is on your equation sheet, by the way, G equals big G, mass of whatever planet it is that you're standing on or you're above, divided by the radius of that planet, in this case Earth, plus the height squared. So at this point, it's plug and chug. Now you do have to work this one though, because it's on the take home. Mass of the Earth, we got a problem. Earth's radius, see if you catch it. I just realized third hour didn't catch this. And G, third hour is pretty bright, but this one got by him. And then H, this is the pointing arrows version of physics. What's my mistake? If I plug those numbers in, what's my mistake?
It means
100 meters.
You guys were quick on the draw that time. You see the problem, and it's right here. Yeah. Kilometers. Oh, I'm getting nervous because I'm running out of time. It's kilometers here. You are stuck with the units of your constant. And the units of my constant here is not kilometers, but meters. So I've got to, good grief. So this is what happens when I get nervous. I've got to put my OCD kicks in. I've got to put meters there. So I've got to convert this one, not 38.97. I got to say, I could say, okay, 38.9, 38,000, right? 38,970 meters. And then for this guy, I got to plug in 6.378. I got to go 4 siggies times 10 to the 6th meters. So it's 6.378 million meters for the radius. So you add those two numbers up. Obviously, the radius of the Earth dominates, but it does change slightly. So it's enough to change because you're squaring it. So it's enough to change his G. And what you'll find when you plug the numbers in, got a minute left, you'll find that his G, I think you should get 9 point, that's what my girl's got, second error, 9.78 meters per second squared. I mean, it's Avery. I got Avery and Aspen. I mean, I have to assume they're right. They don't make a lot of mistakes. So that's what they got. Somebody else got 9.64. I think he's wrong. 9.78. So it's, in other words, it's 9.81 at the surface. You go up 37, about 25 miles, and it drops down to 9.78. Not by much. Now you go up 200 miles, it drops down to 9.6, 9.5. Well, more like 8.9, I think, where the space station is. But it's still pretty close. Remember, they're back in free fall. We'll discuss that more in June. All right, the space station stuff. So there's that one. Probably want to see a little more work than that, although that'd probably get you credit on a take home. Take home, I'm just checking to see that you gave it a real good shot. Now, a test, that wouldn't work. You'd have to actually do the numbers. But you might want to just practice doing those numbers just so that, just so you're good at the old calculator on the test day. All right, we are at 2 o'clock. That was a good session. We got two more. So I'll see you guys. If you have a question, stick around. Otherwise, I'll see you tomorrow. Usually I always a question. Okay.